Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Whimsical Wavelengths is back. Here is the last episode of Season 2. By the end of this episode, all variables will have been observed. The models will have been converged, hopefully showing the residuals are within tolerance. Okay, that technobabble was all meant to show that I'm working on getting a lot more guests lined up. New stories in the pipeline. We're reflecting on what worked and what didn't in Season 1. It's already been a journey. Special thanks to those who did give me feedback throughout the year. It was needed. Embrace the terrible puns and jokes and don't apologize for them was just one piece of advice I got. Or to put it another way, don't be overly Canadian, eh? I can make that joke because remember, I am Canadian. And of course, a special thanks to all the guests that agreed to come on the podcast. Some without any tie to someone I know. They took a chance to share their work with me. An unknown podcast showing up in an email or random call out and ask. The next 3 episodes, at least in this same time frame, will be Encore editions. Some of my favorites from the inaugural season. And then on September 15th will be the start of Season 2. Just in time for my birthday. Yeah, last year I started the podcast on my birthday. What better way to celebrate? Oh, and one last thing. Send the show an email or a comment on social media. Let me know what worked and what didn't. Maybe a topic for next season. For instance, do these solo episodes that take a broader historical tact work? It is the listeners that make a podcast work. It should always be more than the host talking into the void. Okay, on to the show. This is the sibling episode to the last one. The rise of leaded gasoline. And some history of lead, the automobile combustion, and the person responsible for the chemical component, Thomas Midgley. By the way, I know I did mention that he was killed by his last invention in 1944, but not what that invention was. So let's close that story before moving on. Thomas Midgley contracted polio in 1940. Disabled, he created a contraption to help him get up and out of bed unassisted. Unfortunately, he died, tangled up in it. A sad way to end a career of inventions of science, even if some of those inventions led to terrible consequences for the world. This time, the story starts with Dr. Clair Patterson, a geochemist, born in 1922, before lead became ubiquitous in gasoline. He graduated high school young at the age of 16 in 1939. According to his biographical memoir, it was a chemistry set that he got from his mom as a kid that pushed him into a life of science. Parents, I'm pleading with you, get your kids science stuff, please. I know, my monsters, my kids would rather throw themselves down hills and fall out of trees. At least they're testing gravity, right? Also, he went by Pat with his friends. I'll just keep using his full name or Dr. Patterson. Well, graduating early from high school led to a degree in chemistry in 1943. Completed a master's in molecular spectroscopy, and he got married in 1944. After graduating, the war was in full swing, and the race for the bomb was on. He did try to enlist in the army, but his science chops designated him as an asset to be kept at home. Therefore, both Clair Patterson and his wife, Laurie, also a chemist, became civilians working on the Manhattan Project. No, not in New Mexico designing the bomb like depicted in the movie Oppenheimer. Instead, they got to work on the problem of concentrating uranium. A uranium-235 electromagnetic separation plant in Oak Ridge, Tennessee. The Oppenheimer movie actually includes the scientific leader for this technology, Dr. Ernest Lawrence. It all started with Ernest's invention of the Caltron, a mass spectrometer. The Caltron ionizes and accelerates a sample by electric fields. The ionized sample can then be deflected by magnetic fields. Since the ions of different isotopes have the same electrical charge, but different masses, the heavier isotopes are deflected less by the magnetic field. and it takes more force to deflect something with more mass. This causes the original beam of particles to separate into several beams by mass based on their isotopic makeup. Separation means you can concentrate different isotopes, in this case, mainly uranium, and this is the method that was originally implemented to concentrate uranium in the Manhattan Project. Although, shortly after the end of World War II, the United States of America made the switch to the same method used today. It's also been in the news recently, centrifuges. Anyway, back on track, at least briefly. The experience gained in the Oak Ridge plant provided the background Clair Patterson needed for his next big scientific quest. This twist of fate, with the use of the mass spectrometer, likely set up his entire career afterwards. The Manhattan Project to the age of the Earth, which is where we're going. It's all about radioactivity. And radioactivity was understood back then. It was already determined that it happened at predictable rates and formulated it should be possible to date material based on their parent and daughter products. In other words, the element before radioactive decay, the parent, and the daughter, which is the product that results from radioactive decay. For Dr. Clair Patterson, this was uranium to lead. You know, in truth, geoscientists really will date anything. Okay, to radioactive elements. Ideally, everything wants to be at its lowest potential energy. It really doesn't matter if that thing is a ball on a hill or the nucleus of an atom. Inside the nucleus of an atom, there are protons and neutrons. Protons want to repel other protons, yet they're all stuck there together in close proximity, and the neutrons stick them together through the nuclear force. The imbalance between forces in the nucleus can give rise to instability and radioactive decay through releasing of energy and mass. In general, there are three ways unstable atoms undergo radioactive decay. Alpha decay. The nucleus emits an alpha particle, which is just two protons and two neutrons, basically a helium nucleus. This is the primary type of decay for uranium isotopes that we're covering here as part of this story. Each alpha decay reduces the atomic number by 2 and the mass by 4. Beta decay. This is where a neutron in the nucleus changes into a proton, or vice versa, releasing an electron or positron. This changes the element's atomic number by plus or minus 1, but keeps the mass nearly the same. And then there's gamma ray decay, which is a high energy emission of a high energy photon. There's no change in the protons and the neutrons. It just releases excess energy, usually following alpha or beta decay. Radioactive decay is completely random when we're talking about an individual atom. And in general, it's probabilistic. Half-life is best defined by that it is the time required for exactly half of the entities in a sample to decay on average. The earliest suggestion that it should be possible to date rocks on radioactive decay was made by Ernest Rutherford way back around 1907, 1905. Ernest Rutherford, by the way, is one of those giants of science. We didn't yet recognize that there are different isotopes at that time, even if we understood that uranium became lead. That would take an additional 7 years. To be able to date material based on radioactivity requires precisely knowing the amount of starting element called the parent, as I previously described, and the amount of the final product called the daughter. The precise amount? That's hard to do. Is that foreshadowing? Stating the obvious? There are a few other assumptions that go into dating rocks, like that the rock is a closed system, meaning the amount of both parent and daughter material have not been changed, removed, or added to the rock. For example, water can flow and dissolve minerals and remove them. Removing daughter or parent material will invalidate the dating procedure. Just to give a different example than lead, most people remember or are familiar with carbon-14 dating because it dates things closer to our time. This, say, works for the last 50,000 years-ish. It can be argued it can push back a little further, but even at 50,000 years, it's really difficult. Regardless, let's just leave it there. With the end of World War II, came with it the end of the Manhattan Project. at least a wind down of most civilian positions. Some of the brightest minds the United States of America had to offer went to work on the Manhattan Project. Now they were heading back to academia, and many of them were coming together at the University of Chicago. Clair Patterson was one of these scientists, as he was invited to start a PhD with another Manhattan Project scientist, Dr. Harrison Brown. Dr. Harrison Brown became interested in meteorites and wanted to use them to investigate the abundances of the solar system. So we put together a team to look at different aspects of the problem. Clair Patterson was specifically tasked with developing new mass spectrometer techniques to measure isotopic lead. Like many PhDs, it didn't go as planned. Even sections of my own dissertation did not go as planned. I think it's the standard, it's the norm. As it was during his PhD that he first recognized lead contamination. Although he kind of saw it as a research nuance, complicating the whole thing. Funnily enough, his supervisor, Dr. Harrison Brown, had promised the whole thing would be simple. Duck soup, is in his own words. In the end, Clair's 1951 dissertation did not investigate lead in meteorites in the solar system, but provided lead isotopic compositions from Precambrian granite, specifically zircons, a mineral I suspect eventually will come back around as its own episode, as zircons are used for dating rocks. Throughout all of this, Clair was having trouble obtaining those clean samples for his measurements, i.e., or in other words, there was always lead about on everything, contaminating every sample exposed to air. To accomplish the task of dating a meteorite requires precise measurements. After the PhD finished up, he continued on the original quest with Dr. Harrison Brown as a postdoc, making strides on having less environmental contamination. This was somewhat delayed when Dr. Harrison Brown accepted a position at the California Institute of Technology, and Dr. Patterson followed. Here, Dr. Patterson set the original standards for a clean room to remove lead contamination. See, throughout all of this time, every sample he exposed to air had contamination. At least for a while, he hadn't grasped why. It was a perplexing problem. Where was the lead coming from? There was no data yet of environmental pollution with respect to lead. Because before leaded gasoline, there wasn't the ability to measure minute quantities of lead. In fact, there was little data about pollution in general. These sorts of studies were at the best site-specific in time. With a clean room and a refinement of the techniques, he was able to measure the isotopic values for lead in a meteorite, based on the assumption that the meteorite was a closed system and no uranium or lead was added to or lost after formation. And so therefore, that sample underwent the same formational processes as the Earth in the solar system, i.e. the age should be the same between Earth and the meteorite, and he found that age to be 4.55 billion years old, plus or minus 0.07. In 1953. This was huge, is huge. In his own words, true scientific discovery renders the brain incapable at such moments of shouting vigorously into the world, "Look what I've done! Now I will reap the benefits of recognition and wealth." Instead, such discovery instinctively forces the brain to thunder, "We did it!" in a voice no one else can hear, within its sacred but lonely chapel of scientific thought. His headspace was in that chapel of scientific thought instead of pining for credit. It was probably also the reason he routinely listed his name as second on papers published with students to help them advance their careers. Let's pause just for 1 second. This, in my opinion, should be the norm. To be fair, some fields have peculiar traditions. In many fields, the senior author, typically the principal investigator who provided the overall direction, secured the funding, and is ultimately responsible for the research, is listed last and is the person who had the greatest contribution to the science, including the writing, is listed first. This is not how it is done in my field of geosciences. Maybe because the labs are smaller and therefore the co-author lists are smaller. Traditionally, the authors are listed in order of importance, descending order of their amount of work on the paper. So usually, in my case, the supervisor or the principal investigator is second on the list, and the graduate student who presumably wrote the paper is first. And the way I like to look at it is, remember, the professor has already made it. They have their career. And it's better to build the careers of the next generation. It also helps their career in the long run, as that gives them people to work with, and not to mention more and more citations. It is also recognized by people in your field if you break that norm too often, even if the funding bodies sometimes don't. There are many cases where the principal investigator does put their name first, and there's good reasons for it, sometimes. Especially back then, though, it was a really common occurrence. Remember, once part of the system, many professors end up becoming essentially managers. The grad students are normally doing the bulk of the scientific work. So honestly, I applaud Dr. Patterson for doing this, especially way back in the 1950s and 60s when this wasn't as normal. With the new advancements, Dr. Patterson turned to using lead tracers to investigate the Earth's evolution. A paper published in 1962 investigated lead in ocean sediments. From here, the lead in the environment starts to spin story webs. They showed that there was an increase in the lead in the environment each year that was 80 times the rate of the deposit in the ocean sediments. That was big. It's a big deal, although it was a rough calculation, large error bars, and needed more data. But this was the first paper that Dr. Patterson published noting that environmental pollution of lead, that the anthropogenic amount of lead entering the system was significantly higher than what was stored in older sediments. In 1963, a paper with Mitsunobu Tatsumoto, I'm sorry if I'm pronouncing that wrong, showed deep ocean water contained 3 to 10 times less lead than surface water. In general, the reverse trend is true for most elements. Then came a paper called Contaminated and Natural Lead Environments of Man. This is where things kind of go off the rails. From the introduction, the paper says, this suggests the average resident of the United States is being subjected to severe chronic lead insult. To quote one more paragraph from the summary of the paper, 0.25 parts per million of lead in the blood has been regarded as more or less natural for a long time. But such a level seems actually to lie between an average natural level of about 0.0025 parts per million and an acute toxic threshold of 0.5 to 0.8 parts per million. This suggests that the average resident of the United States is being subjected to a severe chronic lead insult. Okay, the data at this point wasn't definitive, but it was the next best thing. In science, the next step is to reproduce the results and or test the same concept from a different angle. However, some were having none of it. A medical doctor, Robert A. Kehoe, MD, was working at the Kettering laboratory. Okay, when I read that, I was like, wait a minute. The problem with writing these two episodes with some time apart is I've already kind of recorded the first. In the late 1920s, Dr. Robert A. Kehoe was working for General Motors Research Corporation on a newly developed industrial compounds, namely tethyl ethyl lead and Freon. CFCs, under Charles Kettering. Well, he was like the manager that kept everything going and actually hired Thomas Midgley, who came up with the formulation for tethyl ethyl lead. Well, Dr. Robert Kehoe brought together a multidisciplinary crew to study and ultimately help with the making the product so people would no longer die in their factories. He didn't take kindly to this new research, this new paper. It went against a lot of what he had been saying for years. The issue, it was basing lead levels off of recent contaminated levels. He wasn't able to go back to earlier time frames, and those early time frames didn't have the sampling techniques to be accurate enough, namely the 1920s. So he had no idea what the actual natural numbers were and should be. But he wasn't going to go down without taking a few swings. Okay, a brief thing. I don't actually know if the laboratory in question is named after the manager that assembled the team that gave us leaded gasoline and CFCs. But all the players seem to be involved. University isn't exactly forthcoming via their website about the history here. And Dr. Robert Kehoe labeled our protagonist as more of a zealot than a scientist. He really didn't hold back. Academic tit for tat. They do happen. But it's only through writing instead of televised debates. Debating is a very different skill set. To rebut much of the scornful comments with his revised manuscript, Dr. Patterson wrote, "The enclosed manuscript does not constitute basic research, and it lies within a field that is outside my interest. This is not a welcome activity to a physical scientist whose interests are inclined to basic research. My efforts have been directed to this matter for the greater part of a year with reluctance, and to the detriment of research in geochemistry. In the end, they have been greeted with derisive and scornful insults from toxicologists, sanitary engineers, and public health officials because their traditional views are being challenged. It's a relief to know that this phase of work is ended, and the time will soon come when my participation in this trying situation will stop." Well, his involvement, thankfully, did not stop. After correspondences pleading the case with emphasizing the data, he appeared to inform Congress, emphasizing the difference between natural and normal lead levels. To me, it's instantaneously understandable. Everyone under the same pollution levels can have a normal but high level of contaminant. The natural level would be without that pollution in the first place. As a co-author, part of a study in 1969 showing lead levels higher in the snow and ice since the Industrial Revolution was another feather or brick to the pile. In 1971, the National Research Council released a report, Airborne Lead in Perspective. To take an excerpt from their conclusion, even though all the other scientific data is starting to pile up. In this technological era, the use of lead compounds must be regulated to prevent possible toxicological effects to man and his environment. The problem of lead pollution will ultimately be solved by economic and political means rather than scientific means. The extent of regulation can only be determined after a comprehensive chemical understanding of the clinical and biological response to man to lead compounds is achieved. Okay, that's garble for delay, for definitive evidence. Ugh, I get it, science is about pushing the boundaries, but when there is clear data, you gotta pause and reflect and change course and study the change. Many want to double down on just staying the course, however. The panel involved in the report was also accused of being heavily weighted towards industrial scientists who had, let's say, biases, much like the previous one we were just talking about, who was, in fact, employed by the Ethel Corporation at one point. Despite all of this, in 1973, the Environmental Protection Agency, enacted by Richard Nixon, yeah, that Nixon, another podcast to binge listen about Nixon and completely unrelated, is Slow Burn, the first season. That first season is all about Watergate. No, I don't get anything from this plug. I'm just doing it because I thought it was amazing. Anyway, the EPA, or the Environmental Protection Agency, announced a staged and slow reduction in lead in gasoline by 60 to 65% in staged steps. It was a start. Dr. Patterson wasn't done. He applied his geochemistry background to archaeology, Peruvian skeletons that were dated to 1600 years before present. Assuming the skeleton bones represented a natural lead concentration, it suggested that modern Homo sapiens had 700 to 1200 times increase in lead over and above that natural background. Dr. Patterson would go on advocating removing lead in the food industry as well, eventually getting appointed to government boards, etc. The data was repeatable, so eventually he rode out the bumpy waters. Challenging the industrial consensus on lead was not easy. He was called names, had problems publishing in some journals because of it. But in the end, the data was consistent from every angle. Every angle he tried. Well, Thomas Midgley, who started all of this off, was a good scientist in the sense of testing the method. He couldn't view the problem in a more long term, what it would mean. And remember, he was a cog in the machine. Dr. Clair Patterson was a great scientist, But more than that, he was able to follow the lines of evidence wherever it led. In part because he wasn't tied to industry directly. It was from academic institutions. Before moving to the final chapter of this episode and wrapping up Season 1, industrial science is real science. The peer-reviewed papers they produce are data. They do, however, have different goals, which may suppress other lines of inquiry. From safety to long-range understanding of what the product or process may do in the future. Today, we've learned a lot from those mistakes in the past. We're still making them, I guess, but we are correcting them so much faster because there's monitoring. Vaping is a good example of something that slipped through and now is well regulated because there's constant science and monitoring. If we want to move forward technology-wise as a society, we need those academic researchers to be free, who can go down the rabbit holes and solve stubborn problems industry can't or won't. The system just doesn't work otherwise. Okay, so the fallout. All of that scrutiny causes more study about lead. That was the byproduct of bringing all of this to attention by Dr. Patterson. The detailed research ended up with a simple phrase: no level of lead is safe. The removal of leaded gasoline from the United States of America was followed by more than a 90% reduction in the mean blood level concentration in Americans between 1976 and 1995. The amount reduced year by year also tracked the reduction in ethyl lead. Today, there's no major amounts of lead in gasoline fuel. The last country to have that problem was Algeria, who finally stopped completely in 2021. Back in 1960, blood levels were not considered elevated unless they exceeded 60 micrograms per deciliter. By 1991, however, that value was set to 10. In 2012, it was cut again in half. A United States of America Center of Disease Control report said the median blood levels as of 2015-2016 were below 1. That's a 60-time reduction since 1960 for everyone, including children. It's a big deal. It's a big change. And it got people thinking about what else changed over that time frame. And one of those things is crime rates. Back in the sibling episode, we already talked about Rome with lusciously lead-laden wine, potentially helping its downfall by lowering the IQ and neurologically messing with the governing classes, the aristocrats. What about the society writ large due to environmental contamination of lead? Were we on a path to Idiocracy, the movie, which is great, by the way? It's a great cult classic. And the story about Crocs behind it is hilarious. But instead of essentially selective breeding, it was the lead. I mean, the correlation is quite strong. There are some studies suggesting a 10% increase in lead leads to an 8% increase in crime. The changes in lead and the changes in crime are offset. Lead affecting children and their development is the logical backed up idea by data in this particular instance, so the difference or lag between the two is about 2 decades. Let that sink in a moment. The lead put out by automobiles likely led to higher crime rates due to neurological damage to children. Yikes. There is some recent meta-analysis that calls some of this into question, but the researchers in the field also question that meta-analysis. Regardless, the debate about our 20th century lead crime trends are truly academic. The lead levels of the 1940s through 70s are gone, and hopefully will never return. Okay, so that's where I'm going to leave it. It shows a really interesting process about how scientific endeavors trying to solve industrial problems created real problems for the world at large. And yet it was still the self-correcting nature of science that got around to showing it was really bad and creating the regulation to remove it from the air and the water. And with that, wraps up Season 1. I can't believe it's done. And no, I'm not getting a vacation. although I will head out into the woods with my 2 monsters at some point during the summer, it is also a time for me to get back ahead of things and get a lot more guests lined up, get everything ready for season 2, because Whimsical Wavelengths isn't going anywhere. So enjoy the next 3 as Encore editions, and be ready for September 15th with the launch of season 2. I'll see you then, and remember, subscribe, reach out on social media, give me some feedback. Now is the best time as I'm preparing to potentially do things differently.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us 6 always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the